Today's discussion is for damped vibration and critical speed of rotor on rigid bearing supports. So in this video, we will see how the expression for um, rotor vibration and critical speeds are calculated, and also we'll understand about the log decrement, peak response, and finally about the critical speed analysis. So let's begin the discussion. Main points to be discussed for damped vibration on rigid bearing supports. As bearing is considered rigid and hence displacement of shaft is not considered at bearings, and also bearing itself has no displacement. Damping of shaft is considered as it is damped condition, then derivation of critical speed, derivation of amplitude, derivation of peak response, then understanding of log decrement, the curve of speed versus amplitude of rotor. Amplitude is the maximum at critical speed and it depends on damping ratio of the shaft. Critical speed for stability checks, and finally damped critical speeds analysis. So these are the main topics for this discussion. Rotor is considered damped and which is supported at bearing number 1 and bearing number 2. Bearings are considered rigid, so there is no displacement of bearing itself, as well as there is no displacement of shaft at bearings. However, there will be displacement of shaft at other locations, and let's say the location, so let's say displacement of shaft in x and y direction, which are perpendicular to the axis of rotation of the shaft. So let's derive for damped vibration of the rotor. So let's assume the following: mass at the center of shaft is mkg, a stiffness of shaft is k1 Newton per meter, damping of the shaft is c1 Newton second per meter, eccentricity of mass from center of axis is equal to eu in meter, angular speed of the shaft is omega radian per second, angular displacement in time t will be omega t radian per radian, lateral displacement of shaft are x and y in x and y axis respectively, then equation of motion of shaft for Cartesian form m into x double differentiation plus c1 into x differentiation plus k1 into x is equal to m into eu into omega square into cos omega t. Similarly, for y direction, m into y double differentiation plus c1 into y differentiation plus k1 into y is equal to m into eu into omega square sine omega t. If z is the complex number, then equation of motion of the shaft for the complex number form can be written as m into z double differentiation plus c1 into z differentiation plus k1 into z is equal to m into eu into omega square into bracket start cos omega t plus I sin omega t bracket close. But e to the power I omega t is equal to cos omega t plus I sin omega t. So equation of motion of the shaft can be written as m into z double differentiation plus c1 into z differentiation plus k1 into z is equal to m into eu into omega square into e to the power I omega t. This is a expression for motion of damped vibration. Now damped critical speed. So equation of motion of the shaft for the complex number form can be written as m z double differentiation plus c1 z differentiation plus k1 into z is equal to m into eu into omega square e to the power I omega t. For natural frequency or critical speed, external force will be 0. So we can write m into z double differentiation plus c1 into z differentiation plus k1 into z is equal to 0. This is equation number 1. Assume solution of the form z is equal to z1 into e to the power lambda t, where z1 is equal to displacement in complex number, lambda is eigenvalue, t is the time. So Z differentiation is equal to Z1 into lambda into e to the power lambda t, and Z double differentiation is equal to Z1 into lambda square into e to the power lambda t. After replacing Z differentiation and Z double differentiation from equation number 1, we can get bracket start m into m into lambda square plus c1 into lambda plus k1 bracket close into z1 into lambda, z1 into e to the power lambda t, which is 0. But z1 into e to the power lambda t cannot be 0, and so m into lambda square plus c1 into lambda plus k1 is equal to 0. So by definition, standard damping C0 is equal to 2 into square root of k1 into m, which is equal to 2 into m into square root of k1 upon m, which is equal to 2 into omega cr, where undamped critical speed on rigid bearing is omega cr radian per second. So damping ratio zeta 1 is equal to c1 upon c0, and so c1 is equal to 2 zeta 1 m omega cr. After dividing by m and replacing c1 in the above equation, we can write g lambda square plus 2 zeta 1 omega cr into lambda plus omega cr square is equal to 0. So lambda is equal to minus zeta 1 omega cr plus minus I omega cr square root of 1 minus zeta 1 square. So two eigenvalue, lambda 1 is equal to minus zeta 1 omega cr plus I omega cr square root of 1 minus zeta square, and lambda 2 is equal to minus zeta 1 omega cr minus I omega cr square root of 1 minus zeta 1 square. So forward damped lateral natural frequency is equal to plus omega cr square root of 1 minus zeta 1 square, and backward damped lateral natural frequency is equal to minus omega cr square root of 1 minus zeta 1 square. So damped critical speed omega dr is equal to omega cr square root of 1 minus zeta 1 square radian per second. So eigenvalue can be written as minus zeta 1 omega cr plus minus omega dr, and for critical speed in rpm can be written as omega dr into 60 divided by 2 pi. So these are the expression for damped critical speed. Now damped vibration amplitude, same equation of motion of shaft for the complex form can be written as m into z double differentiation plus c1 into z differentiation plus k1 into z is equal to m into eu into omega square e to the power I omega t. Assume the solution of the form z is equal to z1 e to the power I omega t, where z1 is displacement in complex number, t is the time. So z differentiation is equal to z1 I omega into e to the power I omega t, and z double differentiation is equal to minus z1 omega square e to the power I omega t. So after replacing z differentiation, z double differentiation in equation number 2, we can write square root of minus m omega square plus k1 into I c1 omega bracket close z1 is equal to m into eu into omega square, because e to the power both side is cancelled out. So we can write z1 upon eu is equal to m into omega square upon bracket start minus m omega square plus k1 plus I c1 m bracket close. So after dividing by k1 in above equation, we can write z1 upon eu is equal to m into omega square upon k1 divided by 1 This means after dividing k, we can write 1 minus, we can write m minus omega square upon k1 plus ic m upon ic ic omega upon K1. But K1 upon M is equal to omega C square. So Z1 upon EU is equal to omega upon omega CR to the power 2 upon 1 minus omega upon omega CR to the power 2 plus I C1 omega upon K1. This is equation 3. So by definition, standard damping C0 is equal to 2 into square root of K1 upon M is equal to 2 into M square root of K1 upon M. Sorry. C0 is equal to 2 into square root of K1 into M is equal to 2 into M upon square root of 2 K1 upon M is equal to 2 into M into omega CR. So bearing damping ratio zeta1 is equal to C1 upon C0. So C1 is equal to 2 zeta1 omega CR, 2 zeta1 M omega CR. So C1 is equal to 2 zeta1 M omega CR. After replacing C1 in equation number 3, we can write Z1 upon EU is equal to omega upon omega CR square upon bracket start 1 minus omega omega CR square plus 2 plus I 2 M zeta 1 omega CR into omega upon K1. Here K1 upon M can be written omega CR square, so 1 will be cancelled. So we can write 2I to zeta F. So if frequency ratio is F, which is equal to omega upon omega CR, then we can write Z1 upon EU is equal to F square upon bracket start 1 minus F square bracket close plus I 2 zeta 1 F bracket close. So let's say magnitude of Z1 is A1 and A1 is a displacement or magnitude from 0 to peak. So we can write A1 upon EU is equal to F square upon square root of 1 minus F square bracket close square plus 2 zeta 1 F bracket close square bracket close. So this is expression of damped vibration of rotor. When frequency ratio is equal to 1, that means a speed omega exciting frequency is equal to a critical speed, and so amplitude at resonance will be also called, this is also called displacement factor or quality factor, which is equal to A1 upon EU is equal to 1 upon 2 zeta 1. So it depends on only zeta 1. Peak response critical speed. Peak response critical speed, we know the amplitude expression of amplitude A1 upon EU is equal to F square upon a square root of bracket start 1 minus F square bracket close square plus 2 zeta 1 F bracket close square bracket close. So after differentiation of this with respect to F and putting 0, this will give the peak response. So on differentiation and simplification, we can write F is equal to 1 upon square root of 1 minus 2 zeta 1 square bracket close, where F is frequency ratio omega upon omega CR. So we can write omega is equal to, for critical speed, we can write omega UR. So peak response critical speed omega UR is equal to omega CR, because F can be replaced as omega UR upon omega CR. So we can write omega UR is equal to omega CR upon square root of 1 minus 2 zeta 1 square. So radian per second. This is a peak response critical speed. Now log decrement. Let us understand about the log decrement. This is a amplitude versus time graph. X-axis is time, y-axis amplitude. At time t1 we have amplitude AT1, at time t2 and it is a AT2, and this is successive. So by definition log decrement is a natural log of ratio of two successive amplitude. So we can write, and time period is TD. So we can write it is ratio of this upon this of log is called the log decrement. So let us derive this. Displacement in complex number we know z is equal to z1 e to the power lambda t, where z is a displacement in complex number and lambda is a eigenvalue, t is the time. But lambda is can be written as minus zeta 1 minus zeta 1 omega cr plus minus I omega dr. So after replacing omega from the equation can be written as displacement in complex number z is equal to z1 into e to the power bracket start minus zeta 1 omega cr plus minus I omega dr bracket close dr into t bracket close. Sorry, t is also multiplied here, so we can write z is equal to z1 into e to the power bracket start minus zeta 1 omega cr into t plus minus I omega dr into t bracket close. So further we can simplify in two forms. Z is equal to z1 e to the power minus zeta 1 omega crt into e to the power plus minus I omega dr into t. But this can be further written as z is equal to e to the power z1 into e to the power minus zeta 1 omega crt into bracket start cos omega drt omega dr into t plus minus I sine omega dr into t bracket close. So this is a sinusoidal waveform, but amplitude is this. So taking the magnitude of amplitude displacement of z as a and z1 as a1, we can write displacement in magnitude a is equal to a1 into e to the power minus zeta 1 omega crt into bracket start cos omega drt plus minus I sine omega drt bracket close. So displacement in magnitude a is equal to a1 into e to the power minus zeta 1 omega crt. So let's say t1 and t1 t2 are two successive time and displacement at1 at2 respectively. Then displacement in time t1 can be written as at1 is equal to a1 into e to the power minus zeta 1 omega cr t1. Similarly for time t2, amplitude at2 is equal to a1 into omega a1 into e to the power minus zeta 1 omega cr t2. So after replacing lambda on the above equation, taking the natural log of both sides in the above equation, we can write log at1 upon at2 is equal to, we can write zeta 1 omega cr into t2 minus t1. By definition, log decrement is delta log of 81. That is natural log. We can log is in ln can be written. Log can be written as ln. So that is same thing, but natural log. So 81 upon 82. So we can write delta is equal to zeta 1 omega cr bracket t2 minus t1. Here t2 minus t1 same, but this is time period. So we can write replace it td is equal to t2 minus t1, also td is equal to 2 pi upon omega dr. So delta is zeta 1 omega cr into td, or delta is equal to zeta 1 omega cr into 2 pi upon omega dr. So delta is equal to zeta 1 omega cr 2 pi upon omega cr, a square root of 1 minus zeta is 1 square. So on simplification, log decrement can be written as 2 pi zeta 1 upon a square root of 1 minus zeta 1 square. So this is expression for log decrement. So if T1 and T2n are the time in the first and last time after n cycle, and corresponding amplitude is AT1 and AT2n respectively, then log or natural ln or log both are same here. So AT1 upon AT1 upon T2n is equal to zeta 1 omega CR T2n upon T21 minus T1, but time period can be written as Td is equal to 2 pi upon omega dr, but n into Td is equal to T2n minus T1. So log T At1 upon At2n is equal to zeta 1 omega Cr into n into Td. Similarly, we can write log At1 upon At2n is equal to zeta 1 omega Cr n into 2 pi upon omega dr. Again, we can write log At1 upon At2n is equal to zeta 1 2 pi n upon square root of 1 minus zeta 1 square. So by log decrement, we can write delta is equal to 2 pi n upon square root of 1 minus zeta square. So log decrement can be written as log of 81 upon 82 n upon n. So if you know the amplitude of first and last or any number, you just take the log and then divide with number of cycle. So this will also give the log decrement, and this is also basic equation of log decrement. So two forms are available for the log decrement for equation. Damped vibration speed versus amplitude curve. So this is a speed, this is the amplitude of shaft, which is damped condition. So one typical value is given here. So with the various speed, if you see at the critical speed is a maximum, other before critical speed it is lower on both end, and so we can say it depends on damping ratio. So if lesser the value, amplitude will be higher of the rotor. Now we have drawn, different value of zeta ratio. There is zeta, different value of zeta. We can say if you see the lower the zeta value, we have highest amplitude at critical speed. When zeta value is increasing, and the amplitude of the critical speed starts decreasing. So these as the value for different damping ratio. So 0.0625, then 0.01, 0.01, zero 0.2, zero 0.5, and 1. So various values are given for damping. The critical speed stability checks. If you see, this is decreasing with the time. This is constant. So this is stable, we can say. This is constant, so still not stable, and this is increasing, so this is not stable. So although this is remains same, amplitude remains same, so we can say the first case damping ratio is positive and log decrement will be positive, and motion is stable as its amplitude starts decreasing. Here damping ratio is 0. Is damping ratio 0, then log decrement is also 0, and so amplitude remains constant. Here damping ratio is negative, log decrement will also be negative, and motion starts unstable because amplitude starts increasing. So this is unstable. This is also considered not safe, and this first one is considered a stable case. Now damp critical speed analysis. We have typical values. This is a damping value. This is a undamped critical speed. This is a damped critical speed. This log decrement. This is peak response. Then this is a displacement factor, and this is separation from the peak response. If you see the separation is above 15%, it is safe. If log decrement should be greater than 0.3, then it is safe. And displacement or quality factor should be less than 8. So these are the typical analysis of critical speed for damped condition. So Hope you understood about derivation of damped for the rotor of motion, then damped critical speed, then amplitude for then log decrements, and finally the analysis parts. So thank you for watching.